So looking at page 3, talking about the properties of summation. And so there's some of them that are obviously simpler than others, and some of them are definitely more complicated, but they're all important. Right? So we'll start off with the most basic one, which is a constant multiple property. So if we take a look at k times a sub I, what that's telling us is that we could factor out the k. Right? And so just a quick example, and I'm not a proof, but just a quick example. So let's say I have the sum from I equals 1 to 4 of 3a sub I. Alright, so that would be 3a sub 1 plus 3a sub 2 plus 3a sub 3 plus 3a sub 4. Now you'll notice here that we have a constant multiple of 3 in each case, which can be factored out. So that would be the same as saying 3 times, well, I'm not there yet, a sub 1 plus a sub 2 plus a sub 3 plus a sub 4. The sum of the terms of the sequence a sub 1, 2, 3, and 4 would actually be just written as the sum of the terms of the sequence a sub I, where I spans from 1 to 4. Alright, with that coefficient out in front. Alright, so again, not a proof, just a quick example. But you can see here how the coefficient contained within the summation becomes the coefficient of the summation itself. Alright. We also have properties like addition and subtraction for summation. Right? We have addition and subtraction rules for limits and derivatives and antiderivatives, so it kind of makes sense that we would have an addition and subtraction rule for summations. Right? It's a sum of a sum, really. You know, so if you wanted to, you could actually expand this out with a quick example. I'll just show you very quickly. I'll do a very, very basic one. So let's say you have I going from 1 to 3 of a sub I plus b sub I. That would be a sub 1 plus b sub 1 plus a sub 2 plus b sub 2 plus a sub 3 plus b sub 3. Now we can reorganize this. We can regroup so that we have a sub 1, 2, and 3 together, and then b sub 1, 2, and 3 also together. Right. So that a sub 1, 2, and 3 would be written as the sum from I equals 1 to 3 of a sub I. Same idea for the b's. And so again, not a proof, just a quick justification. So those are the more basic ones. We also have subtraction. Subtraction is just a special form of addition, so there's no reason to think that this would work any differently. But we do have these more complicated ones. The first one is one that we sort of touched on already, at least the constant multiplier part. But that n coming out of nowhere, that seems to be kind of weird. All right, so let's say, for example, you have the sum I equals 1 to, it really doesn't matter. I'll say 10 of some constant c. All right. So since there's no I written anywhere within the subject of this summation, or the argument, there's nowhere to substitute the 1, then the 2, then the 3, all the way up to 10. But we still will have 10 terms of the sequence, all right? And those 10 terms will be comprised, or composed, whatever the right word is, of the constant c. So I'd have a c for the first term, a C for the second term, a C for the third, fourth, fifth, sixth, seventh, eighth, ninth, and 10th, all added together with understood coefficients of 1C plus 1C plus 1C 10 times is going to give us a result of 10C. All right, so that's where we're getting the product of whatever the upper bound of the summation is and that constant C. We're getting that from the act of expanding this out as much as we are. Try to clean this up a little bit, but doesn't always work the way I want it to. Okay, so then the next one is the sum of the first n positive integers. Right? I representing the index, but also kind of doubling as a set of integers, because if we're going from the values 1 to n in integer form, or the whole number values from 1 to n, whole numbers are a subset of integers. We have what we need to be able to say that if we were to expand this out, you would replace the I with a 1, then a 2, then a 3, then a 4, then a 5, that we would be looking at a set of integers. Not the entire set, but a set nonetheless. So what we would get here is a rule that allows us to determine the sum of those positive integers. Now, I'll give you the short version of where this idea comes from. If you were to expand out, let's say you have the numbers 1 to 100. So, for example, oh, that is not a mark. Okay. What you'd be doing, if we're looking at the integer I, we'd be taking the numbers 1, 2, 3, all the way up to 100 and adding them up. Alright. Now, it's the old story, Carl Friedrich Gauss. I forget the specifics of it, but I always like to tell the story like he was a wise guy in class, where the teacher, would give the students problems to work on, and he would bang them out so quickly that the teacher would say, "Oh yeah, you think you're so good? You think you're so special? Here, why don't you do this?" Figuring that it would take him a while to do, the teacher said, "Just go off in the corner and add up the numbers 1 to 100." And then he comes back like 2 seconds later, exaggeration of course, with the answer, and the teacher said, "Okay, well obviously you cheated. So how'd you come up with that?" And then, Gauss gives this explanation. Now, the story's different, but that's I kind of made it a little bit more Hollywood, but it's not actually too far away from what I just described. So what he did was he took the numbers 1, 2, 3, 4, 5, all the way up to 50, and said, you know what, let me go back the other way, 51, 52, 53, 54, all the way up to 100. Notice that each pair of values added to 101. Alright, so if you look at this, you got the 1, you got the 100. Sum of 101. Same idea for the 2 and the 99, the 3 and the 98, the 4 and 97, and so on. Right? And there would be 50 pairs. So what he did was he said, okay, well, let me take 50 and multiply it by 101. All right, so he got 5,050. But then it begs the question of, okay, well, how do you generalize this? Because that's the thing. You want to be able to not just answer one question with it. You want to be able to answer as many questions as you can with it. All right, so what he said was, all right, well, where did I get the 50 from? Because what he did was he took, again, the 50 times the 101. Well, 50 was the number of pairs in the set. How many pairs are there in the set? N divided by 2. Whatever the number of numbers are in the set divided by 2, assuming it's an even number of values in the set, would give you the number of pairs. All right, where'd the 101 come from? Well, the upper bound of my summation was 100, so I guess I could just tack on a 1 to that. And so put it together and you get this relation. So it's actually pretty clean when you think of it that way. It's just the question of, okay, well, now I need to verify that this works in all cases. So, you know, you change the upper bound to a 10, you change it to 1,000, you change it to 40, 41, whatever, and see that it does give you the same result. Now, because we have technology, we can do this without using rules for the computational parts of it, but we do want to get to a point where we can handle it using the formulaic approach, because we're going to be working with this symbolically, not just numerically. So again, alpha, window, you see the option that looks like a summation, which is option 2. All right, so you're going to pop in some index, doesn't matter what it is, all right, except you don't want a lowercase I, because actually, honestly, I've never tried it with a lowercase I. I just always assumed that it wouldn't work because it's a, the imaginary unit I. So I go with something else, so like a capital I. 1 to 100, and put in the I, and you get your 5,050, which is what you would get if you take 50 and multiply it by 101. All right. Now, if you wanted to take the first n squares, perfect squares, and add them together, you'd have another rule. And perfect cubes, you'd have another rule. And there's derivations that go along with these two. A little bit more complicated, but they are rooted in what we just did. Right? It's kind of cool when you sort of play it out, but sort of a different story for a different day. All right. So for now, we're just going to kind of rely on those relations. Now you see here in example A, number 6A, use the property. Well, this is for number 6 in its entirety. Use the properties of summation and summation formulas to evaluate the sums. The directions are very specific. This is still in the territory of prerequisite material, so it's not like I'm going to ask you a question on a test that just asks you to evaluate a summation. It's going to be part of a broader concept. All right, so we just got to kind of be ready for it when it happens. But for now, it's its own problem. All right, so what I would want to do is first, whenever I'm evaluating a summation, is take out anything that's irrelevant to the summation. All right, so here I'm going to factor out an n squared, all right, because the index, so when I talk about being relevant to the summation, I'm talking about incorporating the index. The index is I. N is not I, fun fact of the day, so I can factor that out. So I'm going to pull out a 1 over n squared. I'm going to have a summation I equals 1 to n. Oops, that's not a good one anyway. And then I'll have an I plus 1, right? So it's the summation of this I plus 1. Now, one of our properties tells us that I can break up a summation by the plus sign. So I could be looking at this as 1 over n squared times, I'll put a big old square bracket there, the sum from I equals 1 to n of I plus the sum of I from I equals 1 to n of 1. Now that 1's a constant. All right, that constant rule is going to come into play. That's the first rule that we talked about here. Well, in the box anyway. All you do is you take your constant and multiply it by the upper bound of the summation. So that's just going to be an n. All right, that sum from I equals 1 to n of I. That's that Gauss rule that we talked about. That's this bad boy right here. So we can pop all of these, or both of these rules in, and then start the process of simplifying. So n times n plus 1 over 2 plus n. All right, so now I have an algebraic expression that doesn't contain a summation, which I can, well, we know algebra, so we can evaluate it using ordinary means. I didn't close my parens here, so let me take care of that. Let me get a common denominator. Boop, boop. put it all together. I can do a little distributed property. Just be careful on an assessment. The directions aren't always going to tell you to simplify. When they do tell you to simplify, obviously you have to simplify. But if they don't, then don't. All right? I'm not saying you shouldn't. I'm saying please do not simplify if the directions do not explicitly tell you to simplify. All right? There's a reason for that. This is the part where I tell you what the reason is, but I'll save that for a later day. All right, so n squared plus n plus another 2n. So I can bring this all together, but I do notice that once I combine things, I'm going to have a common factor. So before I bring it all, consolidate. Let me just do a little bit of this. See, we have a common n up top, which can be factored out. So n over n squared times n plus 3 over 2. N goes into n squared n times. So this would just clean up to be equal to n plus 3 over 2n. Alright, so, there's a lot of stuff here. A lot of funny business going on, but it's very manageable. Alright, it's just the algebra, when people get jammed up on this, it's almost always because of the algebra. So you just got to be mindful of that. And take your time. Alright, so then you look at part B. See, it's the same set of ingredients, really, or at least, let me be fair about it. Same structure, right? But then you see that the n values are replaced with 10s. All right. Well, we have a simplified form for this entire the entire expression in part A. So why not use that? All right. So what that would be telling us is instead of n plus 3 over 2n, how about 10 plus 3 over 2 times 10. So 13 over 20. And then we could just do a quick double check on our calculator. So, I'm a big fan of second enter, the old school way of bringing up the previous computation on TI calculators. So we're going from 1 to, 10. And then we need a fraction. All right, so to get a fraction, if you're not familiar on TIs, TI-84s anyway, alpha, there's a couple ways to do it, but this is the most convenient. Alpha y equals n over d, numerator over denominator. Pop in I plus 1. So alpha, that x squared gives you the I plus 1. And then instead of writing 10 squared, I'm just going to write 100. And it gives me the 13 over 20. So I have the answer before really having to do too much work. But if the question asks you to evaluate, you got to do it the right way, right? Or at least the way that the question suggests that you should do it.